first talk of the afternoon session is by Nergis Mavalvala. It's future directions in gravitational wave detection.
All right, so can everyone hear me? Yeah. So I'm sorry, here I am again. But this time I'm going to tell you a little bit more about the nuts and bolts of gravitational wave detectors. And I'm going to try and build on some of the talks from this morning because there's a lot of overlap in the technologies, okay? So again, this talk is going to pick up where the last one left off. Now I just want to look around the room. I don't think there's anyone here who wasn't at the morning talk, right? So I'm going to skip, I put in one slide just to remind people of what the morning talk was, but I think I can skip that and go straight to where I want to go. So the slide that I was going to skip is this one that just reminds us what happens at a source and what happens at the detector. And then beyond that, I'll just remind people of what LIGO looks like. So LIGO is the Laser Interferometer Gravitational Wave Observatory. 2 sites, one in southeastern United States in Louisiana, and one in the high desert east of Seattle in Washington state. Okay? 4 kilometers long each, laser interferometers. And this silly little picture that I have of the interferometer is just that. It's silly. It's not what the real detector looks like. So I'm going to take you a little bit deeper into the guts of that. Now I'll remind you of the 3 things that you need to know about these detectors, and then if some of you want to go to sleep, you could and still wake up and follow the rest. But the 3 things you want to know is that you need lots of vibration isolation, and our vibration isolation systems look like this. So they have, this is an active vibration isolation system that's capable actually of taking the mirrors of LIGO, and at 100 hertz, which is our most sensitive band, the motion of the mirrors gets down to just around 100 femtometers per square root of hertz. So that's the first thing that happens to the mirrors, is this high isolation. Then the mirrors, 35 centimeter in diameter, 40 kilogram masses, get hung as pendulums. And that's going to be very important for some of the rest of this talk. And the pendulum, again, adds another level of isolation. Each layer of pendulum gives you 1 over f squared isolation. So when you have, this is hanging from 4 pendulum stages, that gives you 1 over f to the 8th. And so you go from having 10 to the minus 13 meters from this system to having another 8 orders of magnitude reduction here, and then the vibrations of the Earth are done away with. And then finally, we have our laser. Now this laser puts out 200 watts of light. But in the end, our signal is generated by using a build-up technique where ultimately in the interferometer itself, we are circulating nearly 1 megawatt of light. So you have to remember those few things are going to be important. We have 40 kilogram mirrors, and we have 1 megawatt of laser light. Yeah, that sort of sets the stage for some of the things we'll talk about. Okay? I should just say the National Science Foundation in the US funds all of this and has done so for 40 years. Okay, I'll remind you, LIGO made discoveries, and so now what I want to do is I want to say, okay, we've done that, what do we want to do next? So the way that the LIGO detectors have been designed throughout their lifetime has been in stages. But let me just show you a little detail now of what the interferometer actually looks like. So you start off with the laser, and here is the beam splitter, and 4 kilometers away are the 2 mirrors. And now you see lots of other little annoying mirrors in the way. So let me talk about each of them. The first ones to look at is this mirror. And this mirror is 4 kilometers from this mirror, so it's very close to the beam splitter. And these 2 mirrors are facing each other. And that makes, just like if you put your own face between 2 mirrors, you see multiple reflections. These 2 mirrors facing each other means this photons in here bounce multiple times. And that's how we get the build-up factor. If you remember in the morning, I had a question about why don't you just fold the arms? Well, we do, and the number of bounces in here is about 200. So it's already about the most that mirror technology allows you to do. Now, similarly, what you do is at the output over here where you measure the gravitational wave, we arrange these 2 arms so that we have destructive interference. That means by energy conservation, all the light should be going back towards the laser. So what we do is we put another mirror here between the interferometer and the laser, and that mirror is facing back into the interferometer, so any light going back to the laser is bumped back in. And by doing that technique, what we do is we start off with a laser that, imagine we have 20 watts coming out into this instrument, and that's what it was during observing runs 1 and 2. We have 20 watts coming in. That power gets built up to 800 watts because of this multiple bounce system, and that 800 watts coming into these set of arm cavities gets built up to 100 kilowatts. Now, you can do the numbers for yourself. If instead of 20 watts, you had 200 watts coming in, which is the ultimate capability of the laser, you can do the math that would be a megawatt in the arms, okay? So that's the details of the detector. And now this is how LIGO has been run. So here was the initial LIGO, and that was the instruments that were run between 2000 and 2010. And then the whole thing was shut down for 5 years whilst we built a complete rebuild of the instrument and detector, and with the target sensitivity of the blue curve, which is the advanced LIGO design sensitivity. Advanced LIGO began its first observing run with the red curves in September 2015. And some of you will remember from all the news stories that we literally had not even signed off that the detector is in running mode when we measured the first event, okay? And so that was done with these red curves here. And our work now ahead of us is to add all the subsystems we need to go from the red curve to the blue curve. And then towards the end of this talk, I will also talk a little bit about the light blue, the cyan curve, which is technologies that we're working on to make an upgrade to advanced LIGO also. And these are quantum technologies, so it should be interesting to at least some of you. So that's how LIGO's been done. So now let's just look at what the actual sort of details of these curves are. So at the very lowest frequencies, initial LIGO was limited by seismic noise, just the vibrations of the Earth. And there, the way that we've made it better is by doing much, much more aggressive and better seismic isolation. So for example, in the first version of LIGO, the mirrors hang from one pendulum. In this version, they hang from a chain of 4 pendulums. And you can see very quickly that you gain by frequency to the 6th power there. So that kind of thing. Now at these intermediate frequencies, and by intermediate here I mean sort of between 50 hertz and 150 hertz, initial LIGO was limited by thermal noise, by Brownian motion of the mirrors. And there are 2 things you can do when you have thermal noise in your system. The one thing you can do, which is intuitive to us all, is you cool it. And that, it turns out, is very hard in these instruments for a number of reasons, not the least of which is that all of the cryogenic technologies introduce vibrations. So you solve one problem and introduce a new one. So we don't do that. We have dialed a different knob, which is that we have used better materials. So you can ask, what does that mean? What that really means is I mean, in this crowd, it should be very intuitive. The way that this thermally driven motion bothers our measurement is when materials dissipate energy into the vibrational mode that we're measuring. So the idea there is to use materials then that do not dissipate energy. And so very high quality materials. So that's how we got from the green curve to the blue curve in these intermediate frequencies, and then the highest frequencies, which for us are above 150 hertz and out to a few kilohertz. It turns out that noise there is the quantization of the laser light. So this is pure as Fethi Oyayden explained. This is just shot noise. And for those of you who know the jargon, this is shot noise. This is essentially to do with the fact that your laser is quantized. You make a measurement with some number of photons, and that measurement has Poisson noise with the square root of the number of photons. So in this case, we just raise the laser power. And that's how you go from initial LIGO to advanced LIGO, okay? And this, by the way, I told you about Ray Weiss as someone that I have tremendous respect for. Do you know this initial LIGO curve that we achieved in 2010 is a curve that he calculated with all of the technologies that was needed in a paper in 1972. And then it took us the following 35 years to make it work. But the vision was there right from the start. So this guy is an amazing experimentalist. and also someone I adore because he was my PhD advisor. What's that? Ray Weiss is his name. You will hear his name, I'm sure, some October one of these years. Okay. Okay. So, okay. So that's how this thing works. Oh, I have 2 slides first. Okay. So after observing run 1, what happened? Remember, we were stuck at the red curves for observing run 1. So let me just say real quick. For observing run 2, this is the 2 LIGO detectors. On the left is Washington, on the right is Louisiana. And you can see that there wasn't very much improvement. Actually, observing runs 1 and 2 are run with roughly the same amount. So at the Washington detector, the improvements came at these higher frequencies. You can see that the orange curve is ever so slightly below the blue curve. And now you'll know from what I said before, you get that by raising the laser power. The problem was we did that, and we were very excited because it's not that easy to do in these instruments. But then what happened was compare the blue curve to the orange curve, and what you see is that these extra noises started to come up, and those are actually associated with the laser beam not pointing very accurately as you raise the power. And so just the pointing jitter of the laser made noise, so we had to back off the laser power, and so this instrument ran roughly the same as it did in the previous run. On the Louisiana instrument, on the other hand, we knew coming out of 01 what this extra noise here was and the lower frequency, so below 100 hertz. And so we worked on that, and you won't believe, but the people who work in labs will be really sort of amazed by this. So that extra noise came from scattered light. Now, I know there's a lot of theory people in the audience, but you should still sort of wrap your heads around this. So what happens is that the LIGO mirrors are among the flattest and best you can actually manufacture. They scatter about 1 photon in every million that hits them. So 1 part per million is the scatter. And that 1 in a million photons scatters out of the main beam, hits some vibrating surface, and enters the main beam again. And to the interferometer, that just looks like mirror motion. And so that's what we see there. And so we had to sort of reduce that scattered light, not by reducing how many photons come off the mirror, but by reducing how many of them re-enter the beam. Okay? So remember, when you hear small numbers like a part in a million, it doesn't mean it's negligible when you have 10 to the 22 photons floating around, right? So that's the other thing. So that's what happened for observing run 2. And then you all know that there was a detection after that. And so now the question is, where are we going next? And I'm going to break this up into the next 5 years, 5 to 10 years, and then 20 years. That's the sort of the outlook. So I'd already told you in my morning talk that there's a worldwide network of detectors. So let me just tell you a little bit about where they are. I also showed you in my morning talk why we want them. Remember the patches on the sky getting smaller? Okay. So where are we at with that? So let me start with, so there are 3 detectors that are really coming up within, I would say, the next 5 to 7 years. Virgo in Italy is the closest to LIGO in terms of joining LIGO, and then Kagra is under construction, and LIGO India is still sort of in the final planning and site selection stages. So here's Virgo. So Virgo is supposed to be very similar to LIGO, and this is what Virgo did in its previous incarnation. Now, all of this is just to say Virgo is getting ready to join the network during Advanced LIGO's Observing Run 2, which, by the way, Observing Run 2 should end at the end of August, which means Virgo has just another month and a half to join, and they're on their way. So let me just show you some very, very recent data from Virgo. So here are the curves for LIGO, the red and the blue, and then the purple guy is where Virgo is operating as of yesterday. So they still have a little bit of noise improvement to do before they're competitive with LIGO, but already with noise at this level, they can start to constrain sky localization. So here's an interesting thing. So LIGO will see a signal, and we'll get all the parameters of the signal from that, including the localization. And Virgo, just even if it doesn't see the signal, will actually constrain its location through limiting process. So it'll be helpful. So that's going to happen in the next month or more. Kagra is the Japanese detector. Kagra is very interesting in its own right. So Kagra has done 2 things that none of the other second-generation detectors dared to do. Kagra is planning to operate cryogenically right from the start. So remember I told you there's this challenge, both of vibrations. There's another challenge, which is the laser power we use is megawatts. The mirrors absorb, again, they scatter about a part per million, they also absorb about a part per billion, which means that they're absorbing in the steady state about 1 watt of light. So cooling them and extracting a watt of light is pretty hard, but Kagra is going to try to do that. And they're in the process right now. They're also underground in the Kamioka mine that some of you will know from neutrino experiments. And so here is a picture a little bit over a year ago of Kagra being built, and you can see the mine flooded. So they have a different set of problems than the above ground detectors do. But the plan is that Kagra will join in first observations around 2018 with sensitivity that won't yet be at the best they can do because they're not going to be cryogenic yet. Okay, so that's the plan. So that's Kagra. And then finally, there's LIGO India. Now, the plan for India is that LIGO is going to build the detectors, same ones we have in Louisiana and Washington, and install it at a facility in India. The agreement is the Indian side builds the facilities and the vacuum system, and the US side, the NSF, provides the glass and the isolation and the lasers and so on. And miraculously, it had been stuck for approval with the Indian government for 2 years. And then about a week after LIGO's announcement last year, it was approved. So it is now an approved project in India, and it's the place right now is where the site selection is going on, which is where are we going to put it. Now, it turns out, when you look at a map and you look at India, it's huge. It looks so amazingly big. It turns out it's a very densely populated place. So finding a 4-kilometer shaped L in the grand country of India is not as easy as it sounds when you look at a map. And so that's not been so easy, but the plan, again, is they would join the global network around 2023 or so. I have to say, every year that I say that, I add a year, so, you have to take these as just, my best guesses. These are not in any way official. All right, so now what comes next? Okay, so that I told you, so we're now out to 2023. We kind of know that these 2 other partners are going to be coming on board, 3 actually, Virgo, Kagra, and LIGO India. What comes beyond that? So let me just show you what are some ideas that people have. And so the next 5-year terms are these things. So these curves now you're used to seeing them. Let me just show you. Initial LIGO and Virgo are way up there in strain sensitivity of 10 to the minus 22 per frequency bin. Advanced LIGO, Virgo, and Kagra are this middle set of curves. They're roughly, you can think of them as a factor of 10 better than the previous. And then there are ideas which was in an earlier slide, I showed it to you as the light blue curve, which are ideas for sort of upgrades to advanced LIGO that will take us to these dashed curves. And then finally, the very solid curve at the bottom corresponds to new facilities. New meaning they have to be in different places than they are. They have to be, most importantly, longer than they are. Remember, the scaling is always the same. The change in length is equal to the amplitude of the gravitational wave, which nature gives us, and the length of our detector, which is a knob we can turn. So that's how what the sort of the roadmap for the next couple of decades could look like. And now I'm going to dig a little deeper into, is this just wild speculation, or is this possible to do? Okay? So why would we do these things? So near term, when we do these simple upgrades, it immediately allows us to explore some physics we can't do with the current detectors. And the most important of those might be that it starts to allow us to look at the equation of state of neutron stars. So think of neutron stars. What are neutron stars? They're a star, but it's funny to call them a star. They're a 10-kilometer large object made up entirely of neutrons at 10 times the neutron degeneracy pressure of a nucleus. So you can think of it as a 10-kilometer, 10 times as dense nucleus. And there is very little known about how to understand the states of matter in those conditions. So our best bet at being able to see that actually comes from gravitational waves. So that's one of the things we really want to do. But there's a whole list of other things. This, by the way, to observe gravitational waves from core collapse supernovae. Remember, supernovae are a completely unknown thing. I'll tell you, most galaxies like our own have one supernova explosion per 100 years. And if we don't make these improvements, we're only sensitive to supernovae in our own galaxy, which means you can just, again, Poisson statistically, we have to wait 100 years on average, and that's not a reasonable prospect. Longer term, with these new facilities I'll show you more about, is we actually are going to be able to map out to the edge of where the first stars begin. So basically to the edge of where we expect to see any gravitational wave sources. So these ideas are limited by our collective imagination, for sure, but there is a much more severe constraint than just how imaginative we are, which is they're also very expensive. Okay? And so I'm going to work our way through whether it's worth doing. So when you look beyond advanced LIGO, we have to first look at LIGO, advanced LIGO itself, and ask what's going on. And this actually will be really fun for everyone, because it kind of tells you, in the end, what limits a precision experiment. Again, usual frequency going from 10 hertz to 10 kilohertz on this axis, goes a little bit below 10 hertz. And here it's in the vertical axis is the strain spectral density again. Advanced LIGO is this black curve right here. And then everything that contributes in some form or the other to this total noise curve of advanced LIGO is shown. What you'll notice is that for almost all frequencies, advanced LIGO is limited by the purple curve. And the purple curve is just conveniently labeled quantum noise. And I'm going to dig a lot deeper into that. So for now, we'll just say this is the quantization of light. Okay? And notice that it actually limits advanced LIGO pretty much at most frequencies. The next most troubling noise source is this red curve here. And the red curve is the thermal noise, not from any other part of the mirrors, but from the mirror coatings themselves. So it's actually from the part of the mirror that's the high reflective thin film coating. So people in this audience are very familiar with thin films. It turns out that their mechanical properties, because of interlayer stresses, they're actually quite dissipative, especially the amorphous coatings, the dielectric coatings that we use. So that's a problem. And then you notice something else that's really fun. The brown curve is the seismic noise, and look, it doesn't matter at all. Below 10 hertz, which is where we don't make measurements, seismic noise simply doesn't bother advanced LIGO. It's a solved problem in that sense, in the sense that we now know how to make seismic isolation good enough that it's not a problem. So what is the problem is actually this green curve here, which is called gravity gradient noise, or also sometimes known as Newtonian noise. And this you'll find really bizarre. I did the first time I heard it. So what is this noise? It's the noise that local gravity, you know, little g, we draw a vector little g in our very first physics classes, and we say it has a value, it has a value of 9.8 meters per second squared. It turns out that local g fluctuates. Why does it fluctuate? Well, simple, a cloud goes overhead, there's a mass distribution that passed by, local g changes, and what does our mirror think? Thinks a gravitational wave went by. So that's the limit, and it's very hard to do better than that. If you go underground, there's some measurements that show you might do a back factor of 2 or so better, and that's part of what motivates the Japanese to go underground. You might be able to instrument around the mirrors with seismic arrays and maybe subtract out by another factor of 2. But beyond that, if you want to make measurements of gravitational waves at low frequency, so below 10 hertz, I have only one answer that we know of. You've got to get off the planet. And that motivates the space detector. Okay, so if that green curve alone tells us why we should do LISA, but there are many other good reasons, but that's the thing. So there's the limit. So now what I'm going to do is I'm going to tell you about, this is what we have for advanced LIGO. If we want to do another factor of 10 better, as I said we want to, what do we need to do? All right, so there are sort of 3 broad classes of things you need to do. For the Newtonian noise, like I said, you can go underground, or you can instrument these mirrors with seismic arrays. And it turns out you can't just use 2 or 3 seismometers. You need 20 or more to completely reconstruct the changes in local G. So it's not a very easy problem. For thermal noise reduction, which is that coating thermal noise, people are certainly, I think cryogenic cooling is certainly being looked at as CAGRA is doing. But even more promising is to go to still lower dissipation mirrors, and among the most promising techniques for that we've come up with are because of recent advances in fabrication, is to use crystalline mirror coating. So these are just multi-layer crystalline Bragg reflectors, and in our case, we're looking at a aluminum gallium arsenide multilayers. Turns out to have much lower, by a factor of 10, lower Brownian noise than the amorphous silica tantalum coatings we're using right now. And then finally, for anything else, remember that purple curve that limits most of the frequency band, you have to do some kind of quantum engineering. There's no way around that. So that's what I'm going to spend a bit of time on that, in part because it's really important, and even more so because it's actually data from my own lab. So I'd like to share some time. And then finally, of course, I think I've already said, making the arms longer is going to be an important part of the future. Okay. So when we look at these third-generation detectors, and there are two versions being looked at right now. In Europe, there is a version called the Einstein telescope. And in the US, there is a version called the Cosmic Explorer. And versions, I mean, these are actually design studies, sort of phase 0 design studies going on. And what you see there are many, many options to consider. And I'm not going to go through all of the details of these. Are all things I've already in one way or the other spoken about in the last couple of minutes. I'm going to concentrate on the very last bit, which is called squeeze light injection. And it turns out no matter what of these options you choose, to make any curve that's better than advanced LIGO, you have to go down this path of squeeze light injection. So let me say a little bit about that. So squeeze light injection is a technology that was being developed for sort of generation 2.5 to generation 3 gravitational wave detectors. But it turns out that the future will be now. So let's say what's going on. This is initial LIGO. On the blue curve, or the red curve, is the target sensitivity. The black curve is advanced LIGO. And because of the increase in laser power between initial and advanced LIGO, we were able to drop the high frequency, the shot noise limited part down. And what we're doing is we increase the laser power, we're making a stronger measurement, right? Our measurement scales with the power, the number of photons you detect. Now, it turns out that this invokes a classic quantum measurement problem, which is when you make a measurement, you must also confront back action. Right? So this then means that because of that increased laser power, at these frequencies, at lower frequencies, we are now kicking our mirrors from radiation pressure. So it's a very simple idea. You have some number of photons. You say, let's make them more because we want a stronger measurement. But those photons carry momentum. Our mirrors hang from pendulums, and so that increased number of photons gives us increased momentum kicks. And this is all quantum mechanical. These are quantum mechanical fluctuations that are both limiting our ability to make the measurement due to shot noise, and in turn, kicking the mirrors due to radiation pressure noise. So this is where we're at with advanced LIGO. We've solved one problem, and we've introduced a new one. In initial LIGO, by the way, this wasn't a problem because the laser power wasn't big enough for it to dominate over the seismic noise and other noises. Now that seismic has gotten a lot better, we have to confront this. So that's the thing. And then let me just say one other interesting little thing, actually. So let's talk about how we're going to deal with that. And I like to say the future is now, because like I said, this was something we were thinking of for future generation detectors, but it's experiments that we are doing now. So let's do a little thought experiment. Some of you in the room are quantum optics people, but many of you are not, so this might be fun for you to do. So imagine we have a simple interferometer, and it's a very ideal interferometer. You have a laser, you have a beam splitter that splits half the light and sends it to this mirror up here, and the other half of the light gets transmitted to the mirror on the right. These are good mirrors, they're perfect reflectors, they reflect the light back, the light interferes. And now, I can arrange the path length of each of these two arms such that I have perfect destructive interference at the output. What does that mean? That means no light comes out at this output here. So my first question is, where does the light go? It goes back to the laser. Light doesn't just disappear. So all of the light goes back towards the laser. Now let me ask you another question. Imagine that there's noise on the laser. Imagine that the laser is jittery. Where does that noise go? It goes back to the laser. Noise photons don't know they're noise photons and not good laser photons, so it also goes back to the laser. So in that reasoning, you would say that I could make a perfect measurement at the output here. All the laser noise goes back to the laser, and I'm good. So first question you have to ask is, well, where does the signal come? The signal comes from the motion of this mirror relative to this mirror and comes out here. So now let's ask what's really going on. That explanation that I just gave you is what classical light would do. In quantum optics, it turns out that the beam splitter used in this configuration is an open quantum system. It's got these 3 ports are in use, but this port is open. And what happens to open ports in quantum systems? Anyone? Vacuum. The electromagnetic vacuum is just sitting there waiting to race in. So let's see what happens. So here we go. We start off, and the electromagnetic vacuum is now entering this interferometer through this open port. And you can see that this is a vacuum state, because just from our introductory quantum mechanics here, it's a minimum uncertainty state. X1 and X2 you can simply think of as a combination of the amplitude and phase of the light, okay? But then these are just the Hermitian operators that correspond to those. Okay, and it's a vacuum state because it's centered around 0. If it were a coherent state, it would be the same circle, but sitting at the end of a stick, right? So that's how we think of this. This vacuum state enters the interferometer, and by the symmetry of the beam splitter, for the same reason that the laser light goes back to the laser, the vacuum state comes back out the port that it came into. Now along comes a gravitational wave, and these mirrors displace, and this little yellow signal phaser comes out. So now look at this, the state is displaced, because now I have some real coherent laser light coming out this output, superposing on this vacuum state, and that's what gives us the shot noise. So this is a very important thing to remember and notice, because if I were to squeeze the laser light, it would do me no good, because it's all coming from the vacuum state at this output. So what can I do? Instead of trying to squeeze or make any kind of special exotic quantum state of laser light, I have to make an exotic quantum state of electromagnetic vacuum. Okay? And so I do that. Let me just say, it turns out that the radiation pressure noise that I talked about comes from the same vacuum state that arrives at this mirror here. It superposes with this extremely strong, bright laser field and kicks the mirror. So it's the same vacuum fluctuations kicking the mirror by superposition with the bright field here. Okay? Now, what can we do? So I can prepare a state like this. And notice what's special about this state is that it's called a squeeze state. It in no way violates Heisenberg. What it is as long as the area of this ellipse is the same as the area of the original circle, but just redistributed, that's a valid quantum state. And so our challenge is to make such a state in the lab. Then what we would do is we would inject it into the interferometer, and now look what happens to the measurement. Now we still have our signal photons coming out here, but superposing instead on this state, which in this direction, just along the signal direction, has lower noise. Am I violating Heisenberg? No, because along the other axis, I have more noise. So if I made a measurement along the other axis, along the X1 axis, I would get noisier. But this I'm allowed to do. This is just redistribution of uncertainty. And therefore, that's the trick we play. This was an idea that was introduced amid a fair amount of controversy, by the way, in 1980 by Carl Caves, who was at the time a graduate student of Kip Thorne's. All right, so here's the experiment. No need for any attention to details other than that. Here's the laser. Here's the interferometer. At this output here is where I would measure the gravitational wave signal, literally at the output PD photodetector here. So what we do is we make this squeezed vacuum source, which is basically a source of entangled photons. We inject that into the interferometer, and if we do it right, we should see improvement. And indeed, we do. So this is data that was taken with the initial LIGO interferometers in 2011. The red curve is what we had for initial LIGO before we injected these squeeze states. And you can notice that it was shot noise limited above about 150 hertz. So right where you can see where the red line goes up like that. Then we injected our squeeze states, and we were able to see make an improvement of about 2 dB or 25%. And that's sort of seen as sort of the evidence that this is a good technique to use. We know why it's only 25%. It's because of optical losses. So we're now preparing a system that will allow us to inject squeeze states into advanced LIGO. And when I say the future is now, I really mean it. The squeeze light source is going to be delivered to the observatories in August, right after observing run 2. Okay, so we've prepared a squeeze light source that we're going to deliver to the observatories. Now comes another question. So remember, that's only half the problem. There's the shot noise problem. What about the radiation pressure noise? Is there something we can do about that? And the real question I ask is it a force for good or evil, really? And it turns out it's actually both. We can actually, of course, it's a pain in the ass because it ruins our low-frequency sensitivity. On the other hand, we can use it for doing useful things. And I'll show you in a moment how. So the same Carl Caves who told us about squeezing vacuum states also wrote, in 1980, this paper titled, and I like putting this paper up because it's my all-time most favorite abstract ever. So the title of the paper is Quantum Mechanical Radiation Pressure Fluctuations in an Interferometer. Now here's what I'd like to point you to. There has been a controversy whether quantum mechanical radiation pressure fluctuations disturb this measurement. This letter resolves the controversy. They do. Okay? Now, wouldn't we all love to write a paper like that, right? So again, it was very controversial. Are these real? Because really, what the question being asked is, can the electromagnetic vacuum kick things, right? Really, that's the question being asked. You take a physical mirror, kilograms in mass, and saying the vacuum kicks it. So there was controversy. It turns out that it's on very good theoretical footing, and now we have experiments that confirm it as well. So what can we do about that? So here now enters one of the pieces I introduced at the very beginning of my talk, which is something called cavity optomechanics. Now in LIGO and in many experiments, including ones I'll show you, you have these cavities. What are the cavities? The cavities, they're called optical cavities. There are two mirrors facing each other, right? So you have this light that's circulating around, and if you make the cavity mirrors movable, and for simplicity, let's just say one mirror is on a spring, the other mirror is infinitely heavy and just sits there. Now see what happens. This is now radiation pressure at work, but not in the standard way of me shining a laser pointer at an ant and sending it flying. Now I have a feedback loop in there because of the light that's bouncing back and forth in this cavity. Now, just like for any other resonator, the light in this cavity has a shape like this, a resonance. And it simply is to do with the fact that the light that you pump into the cavity is interfering constructively with the light that's already in the cavity, and you get this resonant condition. So what we're seeing is power inside the cavity, which, by the way, is proportional to radiation pressure. And everyone remembers that radiation pressure force is just P over C, power over speed of light. That's from our electromagnetism 101. And so this is the shape of the radiation pressure force as a function of cavity length. When the cavity is exactly on resonance, which means that it's got 2 pi, n times 2 pi round trips of the light in here relative to the light coming in, you are at the peak. And then you can always detune, so pull the cavity a little bit in one direction or the other. So now look what happens. This is a very neat thing that you all will be tempted to try with your laser pointers later today. Imagine now that you come down to this part here. So you detune your cavity to the blue side. And now what happens is that imagine you move the mirror a little bit outwards. As you move the mirror outwards, that's going to the right, your power drops. That means the radiation pressure force decreases, and the mirror moves back in because it's being pulled in by the decreasing force. The radiation pressure force had it pushed out, mirror moves out, pulls it back in. It's a spring. These are called optical springs, by the way. So these are springs that are simply made by the fact that the mirror is acted upon by radiation pressure force in this feedback system with the resonance. Now, it turns out that the light doesn't respond instantaneously to mirror motion, and that also gives us an imaginary term, which is damping. So for all purposes, this system of light inside a cavity with a movable mirror is like an optomechanical oscillator. Okay? And it has some very powerful uses in gravitational wave detectors, and the one I'll show you is here. So this is now a set of curves for possible advanced LIGO. The green curve is the standard advanced LIGO curve. And then all of these other curves are made by using this optical spring to create resonances in the response of the system. And what you notice right away is that you can use that system to tune the curves to be more sensitive at certain frequencies. You can see, for example, the dark blue curve has very high sensitivity at 200 hertz, but you give up sensitivity at a kilohertz to do that. It's a knob you can turn to tune the curve to be sensitive just to a particular source. If you had a pulsar sitting at 200 hertz and you wanted to measure it, you tune your instrument to do that. And that tuning is done by this optical spring, which actually in the end turns out to be a quantum effect of correlating the shot noise and radiation pressure noise. So that's one example of how this radiation pressure, even though it's a noise that hurts us, you can also manipulate it. Let me give you one other example that might be fun for some of you. You can use this, so you know, as soon as I say it's a force, you immediately, what do all people think of when they think of a force? You immediately think of what can I do with it. Even if I tell my 9-year-old son about force, the first thing he says, well, can I kick something with it, right? So we're going to use it again to do something. So, I should say, by the way, that in advanced LIGO, there isn't a plan to do this right now because the thermal noise would mask that. But in the future, as the thermal noise goes down, you could start to use these ideas in that. But for the moment, there's not a plan. So in our labs, we do measurements with lights and mirrors. And we try to reproduce advanced LIGO. But in advanced LIGO, we have 40-kilogram mirrors and a megawatt of light. You cannot make that in ordinary sort of, you know, university labs. So we try to reproduce that condition by using nanogram mirrors and milliwatts of light. So we do nano-patterned mirrors like these. We also have tried to do this with gram-scale mirrors and tens of kilowatts of light. So you can just, there's the scaling there where you make your mirrors lighter, you can use less light. And here is something that we did. So here's an experiment where we took a 1-gram mirror, we hung it like a pendulum as LIGO does simply for vibration isolation. And then we shone 2 colors of laser light on it. And the 2 colors of laser light we shone, one was blue detuned to make the optical spring. The other color of light was red detuned to give us damping. And what that allows you to do is it makes an optical trap for the mirror. So here is an all-optical trap for not an atom. We're all used to thinking of ion trapping or atom trapping. Same principle, but applied to a 1-gram scale object. And so here's the data. This shows the response of the mirror. So this is the dashed line is the mirror pendulum when there's no radiation pressure. That's just mechanical restoring force from the pendulum, just what we would learn in Physics 101. And then as we dial up the power in the laser, we start to get these resonances, and with more power, we get the resonances to shift out to higher and higher frequencies. So let me tell you what's going on there. So you have a pendulum, and the pendulum's natural frequency was 100 hertz. Then what you do is you take that mirror that is hanging from a pendulum, and at the end of the mirror, you couple it very, very strongly to this optical field. And this optical field has a spring-like force. So now you have basically a mechanical oscillator whose mechanical connection to the pendulum is diluted to the point where it doesn't even have to be there because it's coupling more and more strongly to this optical field. You'll say, why would you do that? Well, first of all, it's nice. It's a controllable field. But more importantly, all the thermal noise that comes down that pendulum connection, you can remove because the optical field is a zero temperature bath. So you can cool the mirror this way. And that's what the data on the right shows, that you can actually take that mirror mode and measure its effective temperature. No cryogenics. This is purely with optical fields. You take a room temperature mirror, and in our experiment, we were able to cool it down to just under 1 Kelvin. Okay? And then since then, we've done experiments with the same system. So here's a 1-gram object coupled to an optical field that's an effective temperature, so its motion is cooled to under a Kelvin. And then we did a further experiment, I won't show you the data for, where we were able to then cool it down to millikelvin. So this is, if you ever want to do quantum states or quantum state preparation for really macroscopic object, this is your technique. So once you have a hammer, everything looks like a nail. So we also went off to the LIGO observatories and said, well, there we don't have 1 gram mirrors, we have kilogram mirrors. This was done again in initial LIGO, so these were 10 kilogram mirrors. And we used the same technique, and we optically cooled the kilogram scale LIGO mirrors down to 1 microkelvin. And what that corresponds to is 230 quanta of energy. So what it says is that we have this macroscopic kilogram scale object that is 200 quanta above its quantum ground state. Okay? Now, in the meantime, since these experiments were done in many nanosystems, nanomechanical systems, people have cooled, nanogram mirrors to their quantum ground state. But for these very macroscopic things, this is still sort of the best we've done. And when advanced LIGO reaches its design sensitivity, that number should come down to 1. So that's where we are. So radiation pressure force can be used for good in improving the sensitivity of the gravitational wave detector, but here's a completely side, effect that we can also exploit with this. All right, let me just close by saying, where are we at then with 3rd generation terrestrial detectors? I'm repeating. So here are some sensitivity curves for what they might look like. Only thing to notice is a busy plot. Only thing to notice is advanced LIGO is way up there. It's the uppermost curve. And so what we can do with different assumptions for technology for these 40-kilometer long instruments are the black curve. And you can choose what kinds of technology improvements you can achieve, and you can get a different series of curves. And that's not the details aren't important. What I want to get across to you is just that these studies have begun now already for things that we expect to be doing 20 years from now. And that's roughly about right, given our experience with initial LIGO. Now, one of the fun things is if you take any of those curves I just showed you, pessimistic to realistic, this allows us to observe 30 solar mass binary black holes as a function of redshift with signal-to-noise ratios of 100 out to redshifts of 10. Now, that is really something very important, because we know that the earliest stars in the universe were at redshifts of 10 to 20. So if we can build these instruments, we are realistically mapping out the entire observable for these stellar mass objects universe. So that's the motivation from the astrophysics side. Now, some of you, I've mentioned LISA a few times. That's the Laser Interferometer Space Antenna. LISA has an interesting mission concept. LISA has 3 spacecraft that shoot laser beams at each other, and they're something like 1 to 5 million kilometers, depending on what design phase they're in. And look at that. That little blue dot is our Earth. So LISA is this triangular formation in an Earth-trailing heliocentric orbit. That's the plan. LISA has had a very, very good year too last year. So LISA has a couple of very uncertain technologies that were never tried before. So we had to fly a space mission to just test out those technologies. And there was a space mission you might have heard of called LISA Pathfinder. And it was only testing out this particular drag-free technology that's never been used before. So I'm not going to give you the details, but there is the Pathfinder. It launched on December 3, 2015. It spent a couple of months making its way to Lagrange point 1, and where this experiment, its mirrors were released, and it was supposed to make a measurement of what is the most precise acceleration you can measure in space, including some of the technologies needed to keep the spacecraft correctly positioned. And that's the result. Again, a little detail, so I don't want to go into too much of it. The vertical axis is just acceleration. Horizontal axis is frequency. This very illegible to you guys, I'm sure, line here is the LISA requirement, and the purple is the data that Pathfinder has taken. So it's done well over an order of magnitude better than the requirement for LISA would be. Very successful. just little over a week ago, it was announced that LISA has been selected for European Space Agency's L3 upcoming mission. So LISA has now suddenly gone from we don't know when it'll be to having an actual launch date. Okay, so it's moving forward, and it's moving forward with a fair amount of international participation, about 20% of it coming from the US. So but it's a European mission. So I want to just sort of finish by saying that we have a brilliantly dark and warped future ahead of us. Look, the current generation of instruments is making progress, making detections. The science case and design for the third generation instruments is ramping up. And prospects for LISA have never been better. So the last thought I want to leave you with is this. So this whole talk of mine, if there's only one message you take away, it's how are we going to build more and more sensitive detectors? So if you want ever more sensitive detectors, here's a nice cartoon of the princess and the pea. Does everyone know the fairy tale Princess and the Pea? All right. So here is a parent reading to their kid, and it says, thanks to this incredible sensitivity, they were later able to use her to detect gravitational waves. Okay, and then there's an actual little sidebar that's a shout out to LISA that says, really, if you want to have her in space for this sort of thing, but the detection apparatus is much worse if she's dead. Okay, so I just want to leave you with this thought and a little bit of humor. We are trying to build more sensitive detectors, ultimately to map out the entire gravitational wave sky. Thank you. Do we have time for questions? I didn't check the time at all. Oh, good. Okay, good. Yeah, so the question was, are they solid-state lasers or are they? They are solid-state lasers. These are neodymium YAG lasers, and the laser is actually quite an interesting thing on its own. So you start off with a very ultra-stable neodymium YAG, sort of 1-watt laser, and then it goes through 2 stages of power amplification. So there's a first stage that takes it from 1 watt to 35 watts, and these are just diode-pumped amplifiers. And then the 35 watt then takes it to 200 watts. And so,
how many kilometers are those L?
The ones that we operate right now for LIGO are 4 kilometers. Virgo is 3, Kagra is 3. So it's between 3 and 4 kilometers. But the third generation instruments that we're looking at are 10 to 40. And then again, there's a lot of geography, or at least socio-geographics, that comes into play. So the European design for Einstein telescope is 10 kilometers and underground. And it's not underground because the science requires it, it's because you can't find an L-shaped 10 kilometers in Europe, too dense. Okay, and underground is easy because in Europe it turns out there's a really interesting difference between the, Europeans and Americans when it comes to mountains. When a European sees a mountain, they say, tunnel, and they drill right through. When an American sees a mountain, they say, let's go around it. So it actually turns out that boring technology in the US, or tunneling technology, is much underdeveloped compared to Europe. So when you do the costing of these things, in Europe it would be not that expensive. It's all very expensive, but it's less expensive to do a tunnel and just go underground than it would be in the US. So the US, we have space, and we can find sites where you can on the ground do 40 kilometers. It still can't be flat. You still have to, bore, but you're boring it at the heights of like 20 meters in, about so. So those are, but so 10 to 40 kilometers.
Thanks. You told us about interferometer-based detectors. In the beginning, you had told us about these bulk metal things. But do you have any comments on any other technologies? Because we hear about these rumors about atomic interferometers, and there is some controversy whether they work or not. I don't know if other people heard about it. Or would these big chunks of metals make a comeback ever?
Yeah. So these are great questions. So the 3 technologies that I can describe are the original Joe Weber chunk of metal. Nobody thinks that those will come back, and the reason is they're actually quite inexpensive. And you say just keep it going. It turns out that what they do is they rely on the mechanical resonant mode of the big chunk of metal, And so those are typically at kilohertz, 900 hertz to 1100 hertz, and they're very narrow. That's the only way you can couple all of that energy to make a detectable displacement of this chunk of metal. And these narrowband detectors, people just don't, even with the narrowest banding you can do, they are more than an order of magnitude not competitive with the interferometer. So I don't think those will make any significant comeback. Okay. Now, on the other hand, atom interferometers are interesting. So the idea there is to use a matter wave interferometer, and the original argument was always, that if you're limited by shot noise, and shot noise, by the way, scales with the wavelength of the light because there is an energy per photon involved. So going to shorter wavelengths is better. Okay? And so why not go to the shortest wavelength we can think of, which is matter wave wavelengths? So there was a lot of excitement about this in decades ago. It turns out it's a very, very foolish argument because on the one hand, you do better with the wavelength, but in every atom interferometer experiment, all you have at the most sophisticated ones are 10 to the 6 or 10 to the 8 atoms. And the noise also scales with the square root of the number of atoms or number of photons. So you cannot compete with 1 million atoms compared to 10 to the 22 per second photons, right? There's just no comparison. Now, that said, there is newly, in the last 5 or so years, some beautiful ideas for using atom interferometers in space, not because of the de Broglie wavelength and all of those original arguments that were shown to be wrong, but because you can use this cold atom cloud as an inertial test mass. It's not connected to pendulums, it's not connected to the ground, it's really just a free-falling mass. And so if you could do the precision in interferometry with no connections to anything else, that would be very nice. And so what I would say about those proposals is the physics is good, the technology is decades away. So I think they should be studied and done, but they have a big catch-up to do.
We now know that LIGO says gravitational waves emitted from a binary of black holes. Now I wonder if LIGO can say anything about some properties of the black holes, like angular momentum during the ring down, maybe, or some other properties?
Yes, absolutely. So LIGO can actually, even with these first detections, which are relatively sort of modest signal-to-noise ratio, you can already constrain something on the order of 7 or 8 parameters of the binary system out of the total of 14 that they are quite well. So what LIGO can do is we know the masses, and you've all seen the paper, so there's uncertainties, and the uncertainties are tens of percent, but the masses, you can know the spins, and you can know the spins both of the components compared to the angular momentum, so you can constrain the spins. We can constrain the distance, and we can constrain, and through the spins, of course, what we're really saying is we're constraining the angular momentum of that. So those are sort of the top level things that you can do. Now, if you want to do more precise measurements, you can do that with higher signal-to-noise events or more of them, just statistically. But really, if you want to get down to sort of some of the most interesting things about black holes at the level of hair or no hair, charge or no charge, those are not possible with this generation of instruments unless we have a black hole binary right in our neighborhood, which I hope we don't. And so for that, we have to wait for the more powerful instruments. But people are thinking about those kinds of questions. There's another experiment, incidentally, that plans to use very long baseline radio telescopes to map out the horizon of a black hole. It's called the Event Horizon Telescope. So you can look that up. It's never going to give you a direct gravitational signature, but it uses some of the properties of light around black holes to constrain those kinds of questions. Yeah.
With this technology, how short the wavelengths you can observe? So
So what is the shortest wavelength of gravitational
That's right. Yeah.
waves that you can observe? So you can see that for most of these curves, so I'll turn the question into frequency instead of wavelength because I've shown most of my spectra as frequency spectra. So you see that at high frequencies, they all turn upwards. Yeah. Okay? Now, why do they turn upwards? Most people who work with shot noise will catch that. They'll say, why does your shot noise go up with frequency? Shot noise is flat. It's white noise. So it goes up with frequency because of those cavities. And the storage time of the light in those cavities is of the order of tens of milliseconds, so it corresponds to 100 hertz. So above 100 hertz, you start to lose signal because you're actually, your light is staying longer in the cavity than your signal will do it. So if you wanted to make a higher frequency detector, you wouldn't choose that as the turning point, as the line width of your cavity. You would actually put it out at kilohertz, make a wider line width cavity. And that, of course, means you get less buildup, and that means your overall sensitivity would get worse. So it's a trade-off that's done. Now, in terms of sources, what do you expect to see out there is another interesting question. It turns out for things that we are pretty sure of, not much. The things that we're pretty sure of kind of cut off at a few kilohertz. Now, there are speculative sources out there that I personally think we should definitely look for, but I would never do it at the expense of the science that we can do with the lower frequency sensitivity. So, if there's some period of time when somehow our low frequency sensitivity is ruined by some other subsystem not operating, I would arrange to put get the high frequency sensitivity good and run there for a while, look for something. But I would never give up the science of the low frequencies to do the high frequencies, at least now. No, there are many ideas with these third generation detectors to build what are called xylophones. And it basically says you have one detector that's optimized for low frequency, another detector that's optimized for high frequency. But of course, that's completely wishful thinking. At $1 billion a piece, nobody's going to populate these, around the planet like, cans of soup. So that's the constraint. Here.
We are looking at the effects of gravity on length scales 10 to the minus 21, smaller than. So it's very small quantum mechanics. And then we are looking at gravity. So in order to analyze your experiments, don't you need a complete theory of quantum gravity?
No. So the question was, don't you need a complete theory of quantum gravity to analyze your experiment? The answer is emphatically no. You need a complete theory of quantized light, because the quantum here is the light. That's why we deal so much with the quantum of light. The gravitational effect and any quantum gravity effect that's happened at the source. And then we're in this far field limit where we're just completely,
Gravity is interacting with the LIGO legs.
The interaction of the light is just with a tiny perturbation on the flat metric. That's it. And it's not, no, you don't need the quantization for that at all. That, in the units, so let me give you a simple example. The place where quantum gravity would matter is the Planck scale. And the Planck scale is 10 to the minus 35 meters. We're measuring 10 to the minus 21. Yeah, we've got many orders of magnitude to go before it'll matter. So. So I just want to say thanks to everyone, and thanks to all of my friends here who brought me here. It's been a blast. Oh, thank you.